But in that case, how about we do this a little different? All right, so yes, tell Ty, sure. All right, next question. Yes? 4. The potential energy of the particle with charge positive Q due to the other 2 charges is, so I assume I have to look at a picture. All right, so the potential energy of the particle with charge positive Q due to the other 2 charges. So looking at this picture, I will need to find a way of expressing, no, I can have it in terms of A. So I just want the potential energy. All right, 0. But let's go ahead and talk about Y, I guess. The electric potential, this one's a do it in 10 seconds and walk away kind of thing. The electric potential from this charge and this charge at this location will have to be equal and opposite. So the net electric potential at the point where charge Q is 0. Therefore, the electric energy at that point for charge Q being at that location must also be 0. For the same reasons that we talked about just the other day. Is this always a thing? No, not always, but it is this time. The amount of potential energy is going to be Q times V, but the electric potential is 0. Right? 2 contributions to electric potential from opposite charges. So is that a simple enough definition? Okay. Or explanation? So there we go. So yeah, I'll choose A. Next, go ahead. 5. All of the following statements about an isolated, solid, charged conductor are correct except, okay, so it's isolated, which means it is not connected to the ground or in any way. Solid, so it's not a hollow shell, it's a solid piece of metal, and it has an unbalanced charge on it. But we don't know anything about its shape. All parts of the conductor are at the same potential. All parts of the, yes, that is true. No, the surface of but everywhere inside has electric field of 0, so it takes no energy to go from one place to another inside the conductor. So the whole thing is raised to the same electric potential. All excess charge resides on the outer surface. That is true. The net charge enclosed by any surface lying entire within the conductor must equal 0. That has to be true. The electric field E just outside the conductor is directed parallel to, that's wrong. It's perpendicular to the surface. So that's one that's wrong. The electric field intensity inside the conductor is 0. So yeah, D is the one that is not true. The electric field is perpendicular or normal to the surface of any conductor at all points on the conductor. That's one of those things that we also don't talk about very much. That's worth maybe a quick flashcard to remember, that the electric field will always be perpendicular to and will be normal to any point on the surface of a conductor. So you have a weird shaped conductor, it doesn't matter. The electric field is still normal at any point on that surface. That's why the charges distribute themselves kind of weird on some kind of shape that object is not, say, a spherically shaped object or something like that. All right. Yes? Assuming the resistance of wire X is, so I have to go look at that picture. Okay. 2 long, straight, parallel wires are held fixed, as shown above. A voltage is applied to wire X, creating a current IX to the right, with the wire experiences a magnetic force, FB, toward Y. So it's experiencing a force this way. That tells me right away that these must be like currents, because that's what would be an attractive force between the wires. All right. Assuming the resistance of wire X is constant, which of the following graphs correctly illustrates the magnitude of the magnetic force on wire X as a function of the voltage applied to the wire? Well, V equals IR. So I determines the magnetic, the force. And if I recall, we're only talking about the current in wire X, not the current in wire Y. So the force is ILB, where this is the force on wire X as a function of the voltage V applied to the wire. So the magnetic field coming from wire Y isn't changing, but the current is increasing. So the force would also be increasing, and it looks to me to be a linear relationship with current. And since the voltage is also going up in a constant fashion, I think is what it said. So it'd be V over R LB equals F. Just making sure I'm not missing anything. We don't know what the... Oh. I can't say anything else. So it's got to be D. Right? L, B, and R are all constants, right? Hold on. Okay, but those are two separate wires. We don't know anything about the current that's in wire Y. So we must assume that we're only talking about what's happening to wire X, but even still, take all that away, look at the graphs. Whether B is changing or not, look at the graphs. It says that we're looking at F equals LB over R times V. There's no way to know it's happening, but at any voltage change for the top wire, this is the relationship that exists, and it's a linear relationship. We don't know if anything's changing with wire Y. But for all intents and purposes, the question isn't about changes to what's happening to wire Y. It's about what's happening between the force on the wire and the voltage applied to the wire. I think they should state in here, though, for clarity, that the current in wire Y is constant or something like that, and they don't. Without it, it could be any of these things if B is also changing at the same time. So it's an ambiguous question. Probably not great. Probably the statistics on this question kind of stink. You know, meaning that there's probably people who get 4s and 5s in the exam who miss it because of what you're indicating. And we've talked about problems too in which, you know, a loop of wire or a wire that's going in a say a square, and we've talked about that because the current is the same in both parts of the wire. We've had problems like that where we get this I squared kind of function in there. So it might make you think of something like that, but we can only take with what we have. And I think the best answer is still D. But even so, we've been at this conversation for 3 minutes. It's a long time to spend on that problem. A long time. All right. Yep.
Can I go over 7 and 8?
I hope so. I think they refer to the same thing, though. Which of the following could be true of wire Y? It carries a current in the same direction as wire X. I think we covered that. So I think that's good to go. It experiences a force directed away from wire X. No, it's an attractive force, so they're pulled together. It experiences a force of different magnitude than the force on wire X. Ooh, that's a good one. What do you think? Newton's third law, right? It has to be the equal and opposite force. So that one's got to be gone. So it's just one. Good? All right, so 8. If the distance between the two wires is tripled, what is the magnitude of the new magnetic force exerted on wire X? This is going to require that we know how the magnetic field is around from the outside of wire Y. It is a long straight wire. Just if you don't know how to get this, you're probably stuck with Ampere's law, right? I mean, it's the only way you'd find it if you didn't have it memorized. But if you have it memorized, it's just going to be mu naught I over 2 pi r. So it degrades as r. We triple it, so it's just going to be 1/3 of the force, right? Because we're not changing the current in wire X. We're just changing the distance. So the magnetic field is going to go down by a factor of 3. So the force is going to go down by a factor of 3. So I think B is the right answer there. Good? All right, Hansa?
Could we do 9?
Moving right along. A proton moving to the right at constant speed v enters a region containing a uniform magnetic field. I'm sorry, I was trying to deliver a message. The magnetic field B is directed toward the top of the page as shown. The direction of the electric field must be, wait, did I miss something? A proton moving to the right at a constant speed v enters a region containing a uniform magnetic field and electric fields and continues to move in a straight line. So, for it to move in a straight line, I'm gonna have to figure out the direction that the magnetic force pushes on this particle, so I can figure out the direction that the electric field must be directed. V cross B suggests it's going to be upwards, so that would be the direction of the magnetic force. I want to apply an electric field that would prevent the particle from being pushed upwards, so I need to be pushed downwards. That suggests an electric field that would have to be into the page to apply a force downwards on the particle. Electric field. All right, it said electric field. The force on the particle from the magnetic field is upwards. So I need to put an electric field in place to keep the particle from acting on that force. So I need another force that's downwards to balance out the upward force in the magnetic field. So I apply an electric field downwards, that'll do it.
Do you mean out of the page?
No, I mean into the page.
Oh, okay.
Do I mean? And don't forget, this is likely to come up. All right, this relationship determines what the velocity is or what the size of the electric field is. Q's cancel out, doesn't matter what the charge is. That would be a follow-up question that I would expect to see, especially if they have more than one of them. All right, enough of that one. Next. Sergio. What's that? All right, so it involves those three capacitors. Got it. Suppose all three capacitors are connected in parallel with a 9-volt battery. Which of the following is true of the electric field between the plates? So all three of these have the same electric potential. So electric potential equals E times D. Between the plates, they all have the same electric potential. So seems to me that capacitor 1 and capacitor 3 would probably have the same size electric field since the distance between the plates is the same. But capacitor 2 is going to have a smaller electric field since the plates are further apart.
Isn't electric field for plates like sigma over 2 epsilon naught sub q over a epsilon naught? So isn't it just dependent on the area?
Say all that over again.
Okay. For a plate, the electric field is sigma over 2 epsilon naught, right?
Yes, but that's in terms of the charge on the plate. That's what sigma is.
I thought it was just, so it would just be q over a. Because sigma is q over a, so q over a epsilon naught.
I hear what you're saying, but I want you to all three of these are being raised to the same electric potential. They're not all charged the same because they all have different capacitances. So, for example, the capacitor 3 will have twice the amount of surface density charge on it as capacitor 1 because it has twice the capacitance. So its value for sigma is different than capacitor 1. Does that make sense? So its electric field is going to be determined by its value for sigma, but it's also got a bigger area. But still, this has to be true between those plates because it's a uniform electric field. And we're raising them all to the same potential. Does that make sense?
Yeah.
So I think you thought too deeply about it. I would just stop here. It's a uniform electric field. It's got to be the same electric field everywhere between the plates. You raise it to that electric potential, so I think it stops there. So does that make sense? Okay. I think you went too far. So it is... it is the same for 1 and 3 and least for 2, so D. Yes? Do I want to? Or can't? What'd you say? Oh, we. Yeah, sure, we. the electric potential along an x-axis is given by the expression V equals AX minus BX squared, where A and B are constants. At what point on the x-axis is the electric field 0? So the electric field is dV dx. So I need to take the derivative first. So when I take the derivative with respect to x, I will get the electric field equals A minus 2bx. And I want to find out when that's 0. So A equals 2bx, so that location should be A over 2b. I think that's the answer.
I forgot that equals DVD.
Yeah, it's not on the equation sheet, but this is on the equation sheet, and they are symmetrical. So don't forget, every integral has a derivative form. Sergio? I don't know. I'm having my confidence shaken after number 15, but we'll see. A uniform magnetic field B of magnitude 1.2 Tesla passes through a rectangular loop of wire which measures 0.1 by 0.2 meters. The field is oriented 30 degrees with respect to the plane of the loop as shown. What is the magnetic flux through the loop? They gave us the wrong angle for measuring the flux. We would actually want this angle, the one that is perpendicular to the area, because when we do flux, remember it's B dot dA, and the direction of an area is normal to the area. So aside from that, I think we would then do, it's going to be 1.2 times point, what is it, 0.1 and 0.2 times the cosine of 60 degrees. Is that one of those answers?
B.
Woohoo! Did you get screwed over by the 30 degrees?
Yeah, this calculating radius.
No. Area is always measured perpendicular to the area. It's normal to the area. So we can't measure the direction of area.
Because it's two-dimensional.
Yeah.
But if it was
Why
like,
did you change that?
Even if it's three-dimensional. What's that?
if it was like a slab and it was three-dimensional.
No, that's why I did.
Flux occurs at a surface. So even if it was a slab, like we've had a problem before where we've had like a rectangular prism, and the electric flux from the charge is still going to be what passes through the surfaces of the prism. All right. A negatively charged conductor attracts a second object. The second object could be which of the following? A conductor with positive net charge. Well, yeah, I think so. A conductor with zero net charge. Yeah, I think so too. And an insulator with zero net charge. No, I don't think so. I think it's 1 and 2. Would you like me to explain either of those? The answer is what?
E. All of them.
An insulator with zero net charge? I don't know why 3 would be a choice. I don't know why 3 would be a choice. I can't answer it. I mean, I can tell you why 1 and 2 are both choices.
Yeah, do you mind explaining 1 and 2?
Sure. If we have a conductor with a negative charge, and we bring anything with an overabundance of positive charge, there's going to be an attractive force between them. I think that one's the straightforward answer. I think the one that's less straightforward is if I bring a neutral conductor, you can induce a charge. The negative charges on my already present conductor will push away the electrons that are on my conductor, revealing a more positively charged surface. This is inducing a charge, and because the positives are closer to the negatives, there will be an unbalanced force that will cause attraction. That's why I'm concerned. You know, something seems, I don't know, can't explain why an insulator with balance of charge, I don't understand what would happen here that would cause any kind of attractive force. Go ahead.
Would there be polarization, even if it's an insulator, like the molecules move slightly?
Technically, no, by the definition of an insulator. Because an insulator is going to have uniform charge distribution spread out, and they say it has a zero net charge. So they can't move from the places that they're at, so there shouldn't be polarization. That's why I don't know. Now, that's a possible thing, and I guess, what you're saying, it's possible that it's made up of polarized molecules like water. And maybe you align them somehow, because water would be considered an insulator, but it's a polarized molecule. But I think it's reading way into it. I'd be more apt to say that the key is wrong, or I don't understand the way this works. But the other side of that, and I'm trying to work the problem the other direction, like, can it influence the charges that are in the conductor in a way that I'm not recognizing or not thinking about? Because maybe I don't have my head on straight, but I don't know. I will have to look it up and research it. I don't have an answer. So I'm sorry, but I think it should just be 1 and 2. So we might need to do some work here. But let's go on to the rest of this, and we'll circle back to number 15. So many choices. Go ahead, I've been passing you over for a while. Please. You should expect better of your teachers, I guess. A metal sphere with radius R1 has a total electric charge of magnitude Q. An uncharged metal sphere of radius R2 with R1 greater than R2 is then connected by a wire to the first sphere as illustrated above. Okay. The separation of the spheres is much greater than the radius of each sphere. When equilibrium is reached, the spheres will halve. All right, so charges are going to move until the surfaces of both metals are at the same potential, right? Do everybody understand that part? So here's the thing. Outside the sphere, the electric potential is Q over 4 pi epsilon naught times R. That's the electric potential on the outside of the spheres. So the amount of charge we're going to have on each sphere is going to move until we get both spheres at the same electric potential on their surface. So I'm going to write this as we have a total of Q, but after a while we'll have Q1 R1 equal to Q2 R2. Right, that has to be what happens when the voltages are equal. But Q1 plus Q2 equals the total charge Q. This is how I would work this problem out. I'm not sure what we're supposed to find out for our answer. When equilibrium is reached, the charges will have charges on their surfaces of equal magnitude. No, they're not going to be of equal magnitude. Charges on the surfaces of equal magnitude, opposite sign. No. Equal electric fields at their surfaces. No. Equal electric potential. Oh, I didn't have to do any of the work. E. They'll have equal electric potentials. Okay. I'm sorry. I wish I hadn't done all that work because it was just select one from the list. I should have looked at my selections more. But yeah, charges will move until you get to the same potential on both surfaces. Yeah. Yes, perhaps. Sorry, it wouldn't stop because there's no force to stop it. It's experiencing a force this way. That force is going to decrease as it gets closer, and the net force will be 0 at the origin. But by this time, it's acquired some amount of momentum, which will carry it past that point. And once it gets over here, you'll experience a force that's going to attempt to stop it until it makes it probably the same distance out. We could probably prove whether it is a harmonic oscillator and even a simple harmonic oscillator, but I think exhibit oscillatory motion is definitely intended here. All right, next question.
18.
Cool, same page. Two particles, each with charge negative Q, are fixed a distance L apart as shown above. Each particle experiences a net electric force F. A particle with a charge positive Q is now fixed midway between the original two particles. As a result, the net electric force experienced by each negatively charged particle is reduced to F over 2. The value of Q is, okay, I see no shortcut. There might be a shortcut that I'm not thinking about. So there's currently a force this way, and it's equivalent to minus Q squared over L squared. I'm just gonna leave out the constant for a minute. But that's gotta be the size of the force. I place a new charge here. That's not a great color. A new charge here that is positive Q, which is gonna generate a force in this direction. The size of that force is unknown, but it reduces this force to half of it. So I think we can assume that this force is half of F. Is that reasonable? So it will be Q over L half squared. And this has to equal negative Q squared over 2L squared. Now the negative sign is unnecessary. I don't know why I have it there. So I think this ratio would be sufficient to give us a value for Q. This will be 4Q over L squared equals Q squared over 2L squared. So is that good enough? Okay. Any question about that? If there's a trick to make that faster, I don't know what it is, or I didn't think about it. I'm doing these on the fly just like you, so. Next one. Yep. 35?
The velocity is always the same.
Well, yeah. So again, I mean, the simplest way, whenever you have and I'll just remind, we did talk about this particular instance, but anything traveling in uniform circular motion, anything, whether it be the particle in the magnetic field or a ball on a string, anything traveling in uniform circular motion has no work done if its velocity is constant. So this, you don't read too much into this. If it's traveling in a circle, the work done by this force has to be zero because it's perpendicular to the displacement. Doesn't change its kinetic energy. All right. Yes.
Could you do number 30, please?
All right. When two identical resistors are connected in series to a battery, the total power dissipated is P. When the same two resistors are connected in parallel to the same battery, the total power dissipated is, I can't do it without thinking it through. So power is going to be equal to two resistors out of the same, so it's V squared divided by R, which is 2R if they're the same. So we know the potential difference is going to remain the same in the next portion of the problem. So so that's the power. That's what P equals. In the next version, P is going to be V squared divided by, in this case, it's going to be 1/2 R. So this is P nu. So if I multiply top and bottom of this by 4, I would get 4 times V squared over 2R, and that's P. So I think the answer is E. Is that good? If you did I squared R, you'd be upset because you have to, the current changes. That makes it harder. Yeah.
Could you do number 34, please?
I don't know everything. A loop of wires carrying a steady current I, initially at rest, perpendicular to a uniform magnetic field of magnitude B as shown above. The loop is then rotated about a diameter at a constant rate. The torque on the loop is maximum when the loop has rotated with respect to its initial position to an angle of. All right. So if I look at this the way I think I should look at it, we have the current and the current magnetic field. So the force on the loop right now, ILB, so force equals L, so L is in this direction if I look at it right there. B is this way. So right now the torque is like 0 because the force on this piece of wire right here is in this direction. And the force on an equal piece over here is in this direction. So there is no torque on the wire now. But if I turn it 90 degrees, I think I'm probably gonna reach a point where I'll have maximum torque because the force in that wire will be perpendicular to the wire. And based on the sine, which is part of torque, I would have maximum torque at that moment. So I'm gonna go with 90 degrees. That'll be maximum torque. Yeah, it's gotta be that one. Is that okay with you guys? Alrighty. Yes, Abhinav?
Going back to the questions previously, the ones that connected, bigger.
The solid conducting sphere of radius r shown above has a charge of positive q distributed uniformly on its
I
surface.
just figured it out.
So I can stop reading now?
No, nobody else has the question, but I'm.
So keep going or?
Yeah, you can keep.
Has a charge positive q distributed uniformly on its surface. The potential at the center of the solid sphere is, it's a solid conducting sphere. All right, so it's going to be whatever the potential is at the surface. So it's positive. So it's got to be A, right? I believe it's A, because that's, yeah.
I didn't see the word conducting. in that
Oh.
word.
Yeah, you'd have to, if you, now, it would not be, if it was non-conducting in a uniform distribution of charge, the answer would not be 0 for the electric potential at the center. The electric field would be 0, but the electric potential wouldn't be, because it takes work to go from infinity to the edge of the circle, to the edge of the sphere, and it would take more work to burrow through to the center. And not even burrow through, just to get through to the center. So there would be this amount of work, plus you would have to integrate the electric field that you get for inside a uniform charge sphere. So, but I'm sure 0 would be one of the answers presented to you. Do you understand why you would have to integrate? Because we tend to get them to think they're the same, the electric field, electric potential are the same kind of thing, but the electric potential at the center is not 0. It takes work to take a positive charged particle from infinity and bring it all the way to the center there. Yeah.
So for an inductor, for the first part of the potential, you're just doing KQ over R, and then when you're adding it, are you doing like the ratio of volumes?
Well, you'd have to first you would do Gauss's law to get an expression for the electric field someplace a distance, say r inside here, which, if memory serves, is 1 over 4 pi epsilon naught q r over r cubed. I think it looks like that, because you get the ratio of the areas, the ratio of the volumes. That's linear, but you would then have to take this and, integrate it from r to 0 to get the increase in electric potential and going from the edge to the center, because you're going against that electric field.
And then you just add that.
Yep, you would add it to this. We did a couple of problems like this. Those are really hard. And we did some where we had like conducting shells like that, if you remember, where the electric field, you calculate the electric potential to get to the edge of the shell, but the potential is the same from the outside of the shell to the inside of the shell, so the potential doesn't change, but then you have to start again and start integrating and go to the center. Those can be tough, because you start ending up with, a couple of these things added together. Yeah.
Why do you add it to the A?
Well, first, remember, electric potential is like work. So it took work to bring the particle from infinity to the edge. I want you to imagine it's like you want to go to the roof of the building. Okay? So it takes work to get an object up the first flight of stairs. Right? That's going from here to here. That was the work done to get there. But then you have to go up the attic stairs, find that door and go up there. So then you add the work to go that next step. So works just add together, so electric potentials just add together too. So that's why you would have a string of these added together for each stage of your movement from one place to another. Because you're talking about how much work it would take to bring a charge from a location at infinity to a location near a charge distribution.
Like a piecewise function in algebra?
Which of the following quantities could be represented as a function of time by the graph shown above? The potential difference across, this must refer to something. A circuit consists of a resistor, an inductor, and an open switch connected in series with a battery. The switch is then closed at time t equals 0. I don't have to do what I'm about to do, but so we close the switch in this circuit. We know that initially the current in the circuit is 0 and it builds to a steady state condition. So as I look at this graph, I know that current in this circuit is going to fit this graph because it's going to start at 0 and build to a steady state condition. But now I should read these close. The potential difference across the resistor. Well, the potential difference across the resistor will start at 0 and is going to build until it reaches a steady state and a constant voltage across the resistor. So I know that this one is okay. And we know the current in the circuit is okay. The potential difference across the inductor. No, the potential difference across the inductor is going to start at V and is going to decrease until it goes to 0. So this couldn't describe the voltage across the inductor. So it should be only 1 and 3 only. Yeah.
Go with 29 ventures.
If the current in the circuit is I at time t, what energy is stored in the circuit in addition to that stored in the battery? Okay, so these answers are ridiculous because you can't add energy and power together. And I'm not even sure what Li is. And this is power, so that's not energy either. So the only one is this one. We don't actually know how much energy is stored in most batteries.
Okay, that's what I was wondering.
I mean,
The amount of energy stored in the inductor.
yeah.
Okay. 31 time constant.
The change in current when the switch is closed is determined by the inductive time constant, tau. If the inductance is doubled and the resistance is halved, the new inductive time constant. The time constant is, it's RC for a capacitor, so is it L over R, I think, for an inductor. So, inductance is doubled and the resistance is halved, so 4. So I often get this inverted. So right now I would probably be saying it's got to be one of these. I'm not sure which one. And I would probably have to work something out to make sure. My gut's going to tell me it's E, but like I said, I would not have confidence in that because I have a tendency to get the time constant thing inverted for some reason. I don't know why, but I'm going to go with that. The idea is that the time constant divided by time gives you something that is unitless. So E. Yeah. All right. Owen, you got another question?
Yes, 28, please.
An air gap capacitor originally has a capacitance C if a thin sheet of metal is placed halfway between the plates of the capacitor without touching either plate, as shown above. The effective capacitance is, we create 2 capacitors in parallel that have half the separation distance.
You end up getting C.
What's that? I'm sorry. I say parallel? I'm sorry. We create 2 capacitors in series that have half the separation distance. Right?
Oh, yeah, you do it.
Okay. A capacitor of capacitance C1 is charged and then connected to another uncharged capacitor that has twice the capacitance as shown above with the switch S in the open position. When S is closed and the system comes to equilibrium, which of the following is true of the charges on the capacitors and the potential difference across them? We know the potential difference has to be the same across them, so it's one of those 2 answers. I think we also know that the capacitor with more capacitance will have more charge. So I think we're talking about one where capacitor 2 has more charge than capacitor 1. So I think that's only this one.
It says the answer is B. I picked D.
It says Q1 is half Q2, so that means Q2 has more charge, so you divide it in half to get Q1.
Oh, I'm an idiot then. Sorry. Trying to go too fast. But yeah, that's got it. You're right. Q1 has half of Q2. So that, yeah. Jeez. That's that's me not reading carefully. Sorry. I said all the right words, and I selected the wrong answer.
I did the same thing. Alan, that's
Give me nuts.
God, that sucks. All right. Was there another one? Go ahead.
21.
A long straight wire of radius A. Okay, so we are looking down the length of the wire, okay. Of radius A carries a current I out of the page, which is uniformly distributed over the cross-section of the wire. The value of, that's going to be the current enclosed, the line integral of the magnetic field around the wedge-shaped path equals which of the following? I just need the current enclosed. So the other side of this equation, basically, mu naught I E N C. So I just need to know how big that pi wedge is and the area of that pi wedge. So that would be the ratio of theta over 2 pi times the area of a circle, which is pi a squared. Wait, no, that's not true. No. Area of a sector is the percentage of the circle. No. Sorry, my brain's just shut down real quick. This is the area of the whole wire. We want the percentage of the area related to the sector. The percentage of that area would it just be theta a squared divided by pi a squared? Would that be the ratio? 2 pi a squared. No, just pi a squared. Why can't I reason this out in front of you?
It helps the answer is
Thanks, Owen. No, it doesn't help. I'm having a hard time, and I'm not sure it's because I'm having difficulty concentrating or what, but I just need to figure out how to do the area of a sector. And for whatever reason, it's eluding me. And if I was on the exam, I wouldn't be freaking out. If I was on the exam, I would probably resort to something stupid, which I hate the even idea of doing, but I can only think of resorting to it.
Mr. Shelton.
Yeah.
Since it's a line integral, do we need to do area or can we do circumference? Like the ratio?
I guess we could do the line integral, like you're suggesting, just going around it. And that would work, but we don't know, the magnetic field isn't uniform around that line integral, which is why I still think area enclosed is the best way to go. Or current enclosed. So this gives me r squared over 2 times theta. So that's going to be, right, from 0 to theta. So that's going to be 1 over a squared over 2 theta. The area of that sector. That right? I think that's right. And then we want to find the percentage of that. So it would be a squared over 2 theta. I'm sorry, a squared theta over 2 divided by, God, I can't even work this all out. The area of the whole thing times the current times mu naught. A squared cancels. I get theta over 2 pi I mu naught. So I guess it is A. That's not clean at all. I couldn't think of how to find the area of a sector. And I resorted to that to find the area of the sector. I know that the current would, since it's a uniform current, it's got to be the ratio of the area of the sector to the area of the whole thing times the current. But I just had a brain fart and couldn't figure out how to do the area of a sector. That actually might be on your equation sheet, how to find the area of a sector, but I don't know. I know there's some stuff on there, but I know I could prove the area of a sector. I just couldn't, in my head, put it together. I don't know why. So, for those of you who are actually trying to get this answer correct, I wanted to take the area of the pi piece and divide by the area of the whole circle. That would give me the percentage of area that there was. And I multiplied by the total current because I was looking for this side of the equation. I didn't think we could do this because we don't have any expression for the magnetic field inside the wire. We could have come up with one. I think that would have been the same amount of work, but then integrating that over that sector, I think would have been harder because we don't have a good way of defining the fact that you would only be able to do that integral for b dot ds if you went and broke your integral up into point from here to here, another point from here to here. So I think that's harder. But I don't know. That was not clean the way I explained that, so I'm sorry. I could, if you would like, clean it up and try from scratch if you wish.
Yeah, can we see it again, please?
Sure. So, cleaning it up and doing it nicer, I want to start by saying, I'm going to just call this the area of the sector. I want to take the area of the sector divided by the area of the whole wire and multiply by I. This will give me I enclosed inside the sector. That's what I want. Because then this is just that half of Ampere's law that's supposed to be equal to mu naught times I enclosed. This is like one of those Gauss's law problems where they tell you to find out what the flux is through the closed surface, but the truth is they're trying to get you to find how much charge is enclosed. Same kind of problem, but for current. Current is only in the sector portion of the circle. So I decided, maybe stupidly, to do the integral of area, which is just r dr d theta, for something that's in polar notation. We've done this a couple times in here. If you run this from 0 to r and 0 to 2 pi, you get pi r squared, the area of a circle. But we only want to do a sector, so I did this from 0 to a and 0 to theta. That should give me the area of just the sector portion based on a radius of a. So the r part will be 1/2 a squared, and the theta part will just be theta. And that's the area of that sector. So when I plug it in up there, I'll get 1/2 a squared theta over pi a squared times I. This should give me the current enclosed. The a's cancel out, drop the 2 to the denominator, and I get theta I over 2 pi. So that's I enclosed. I need to multiply by mu naught for it to be the line integral of the magnetic field across that whole pi piece. So A is the right answer, but that's a long way to get there. I don't have memorized, I guess, the area of a sector. Go ahead.
Couldn't you just use the arc length and the circumference since it would be proportional to the area? Just do like
That might be.
theta over 2 pi r, where the r's cancel, and then
That's what I did.
That sounds pretty reasonable. And, listening to you, there's no reason to think that that wouldn't be a proportional way to do it. So obviously it would work. So this was way more work than necessary. That's a good call. And, in my head, now that I'm thinking about it, you're right, because you can always do the area as a set of concentric rings, and the rings would have to have the same ratio. So that's a good observation. I didn't make it. I wish I had. Would have saved a lot of time.
You actually wrote it down and then erased it.
Huh. Back to this page, eh? The figure above shows the pass of 5 particles as they pass through the region inside the box that contains a uniform magnetic field. Which particle has a positive charge? Ah, jeez. Well, I think we can rule out E, and the magnetic field is out of the page, so the magnetic field is this way. So, which has a positive charge? Well, a positive charge, let's see, velocity and magnetic field, it's going to curve. All right, so it's going to have to be, I think it's B, if my right-hand rule is correct, so it's got to be B. I just tried them for the different ones and saw which ones curve the right way.
Yeah, I found the magnetic force for all of them, but what does that tell you? Like, how does that help you?
Well, because positive particles curve based on the right-hand rule. So, like, let's look at A. A should be experiencing a force this way, but it's curving the other way, so it must be negative. And B is experiencing a force this way, based on the right-hand rule. C is experiencing a force this way, based on the right-hand rule. But it's not curving that way. Right. D is experiencing a force this way, based on the right-hand rule, but it's not curving that way. And E's not curving at all, so screw him. He ain't playing fair. He's supposed to curve. Be like the rest. Be like everybody else.
Would that mean E is an uncharged particle?
It would have to be. Or it's just a particle. Could be a neutral particle. I don't know. Switzerland. Sorry, it's AP Classroom. It's got the little spinny arrow thing. 14. You said 14? Okay.
I mean, you don't talk about it. You get shot. You get shot.
So we've got something that looks like and we're told the current's going in that direction through the loop, and we have a bar magnet north-south. So the magnetic field created by the loop, using my right-hand rule, is this way. And the magnetic field from the bar magnet is also this way. So I believe we'll get it says, in what direction, if any, is the force on the current loop due to the magnet? It'll be toward the magnet, A, because they're aligned. The magnetic fields are aligned, so it'll pull themselves together.